Okay, I hope we are back, because my encoder just crashed and therefore the stream ended. So this will probably be part number 12 now in the image recording list on YouTube. And I hope we can continue now. Keep waiting. Okay, I should have done this before. Okay, something's really laggy. Okay, I hope this will work out without any issues. So we are in the loopclosing.cc file. And the interesting part is probably this run method, where we have this infinite loop. And in this, we check basically in our keyframe queue if we need to do something. And if this is the case, we want to detect loops and correct them. And then sleep a little bit. Of course, after correcting the loop, we also want to optimize all the keyframes in the global map. We saw this method before when we implement the map.cc object. Okay, here we can see how the loops are detected. This is being done using the DBO3 query results. And also we have a normal result somehow. We can calculate a score. And add something to the keyframe database. Which is a member of loop closing, it seems. Keyframe database, it is a DBO3 database type. Did the stream end? Yes, it ended. Thanks for still being here online and joining. I had a problem with my encoder and the stream crashed. Probably it was something that maybe messed up the stream before, because you had like audio issues you wrote in the chat. I hope they are gone now. Let me know if it's still the case. Then maybe in this case I will end the stream today and watch the the recording and maybe try to fix that. But if everything is fine, then I will continue. In any case, thanks for staying with me. I basically just found out that we have in the loop closing data type, we have this DBO3 database type, and we can use this DBO3 database called keyframe database to add new frames. So from a frame we can take the bag of words vector and the feature vector, use it to add it to the database, and then somehow store the results by calculating maybe a score or something. We have the score here. How is it calculated? Not sure. Somewhere it is calculated, which I have missed, which is a DBO3 result data type. Min score accept. Where is this? It's probably also a member variable here. Min score accept. Okay, so this is a parameter set to tell us at which DBO3 score we accept a frame as a loop closing candidate. And if we accept that, we return true from this function. And the loop correction . Okay, the loop correction is being done using the perspective endpoint algorithm. And here's also some Lie algebra magic, it seems. Exponential map. Unfortunately, I do not see this code hint, which tells me if this is from Lie algebra to Lie group or from Lie group to Lie algebra. But I suppose, given that we have a minimal representation for R and T, this will probably go from Lie algebra to Lie group. Ah yeah, sure, it will create an SE3 here for us. Yes, so this will create a rotation matrix, this will create a translation vector, and from this we can create an SE3 Lie group object. And we can use that using this matrix operator and create a sim3 object of that. You can set the scale and then compute an optimized pose. Using this as an initial estimate, it seems. Okay, so this loop closing functionality is probably very interesting to look at as well. But once again, this will be more interesting, I think, when we are actually running that on a dataset. Okay, so this is it with loopclosing.cc and loopclosing.h. So let's add it here, front end loop closing.cc. Then after loop closing.h, we have minimal image.h. This one is already implemented. After that, we will have a new file called nanoflan.h. This is probably the nano fast library for approximate nearest neighbors that we have just discussed before. So let's paste the code. And this code has a whooping lines of code number of 1352. And this is only the header file. With the meta programming. Okay, seems interesting, but we will skip that here. Let's just see if we have an implementation. We do not have an implementation file for that. That's why we can continue with another file, add new file called pixel selector 2.h. Pixel selector 2.h. Let's copy the contents. Okay, so the pixel selector will select points from an input frame. Who would have thought that? And the way we can select points in the images, they are manifold, and therefore I would say that probably there are multiple variants implemented here. Grid max selection. Make pixel status. Okay, it seems that I'm wrong and there is only one kind of pixel selection strategy. But let's take a look. Let us create this CC file. So in the front end, in the source directory, we'll create a pixel selector 2.cc file. And paste it here. So we have the select method, which will create a vector-free I, which will probably select only one point, I would say. Make maps. Which will return a number of half sub, which is related to num half, which is n0 plus n1 plus n2. What is n? N is a 3D vector, which is returned from the select method that we just looked at. You can also make histograms using a frame Hessian. Okay, and we see that this pixel selector is deterministic. So when we run that pixel selector on the same image multiple times, we expect to get the same answer every time. No randomness. Which is interesting for debugging and for testing. Okay, so let's save that. And let's add this file, like the loop closing, front end pixel selector 2.cc to this CMake lists file. And with this, we are finished with the front end folder. The last folder that is left is this internal folder, which we have for the include directory as well as for the source directory. And in this internal directory, we will have something that is missing yet, which is the calip hashing. This is something we saw quite some times already, and now we need to create this. So this is the calip hashing dot, in this case cc, because I again started with the implementation instead of the header file. And here also calip hashing.h. So the calip hashing is again related to our camera intrinsics, but it will also include the hashing. What is the hashing? Something related to the second derivatives, but I think it's not meant like that in the code, but rather as an element in the optimization. So let's add Twitch here. And let's skip those values because they are mainly related to fx, fy, cx, and cy. In this case for every level. And I think we know what this is by now. This will also include the gamma function, so our photometric calibration, and some optimization related fields like a step backup, value backup, and value. Okay, so this is the calip-hashing.header file. Now let's go to the calip-hashing.cc file, which does not exist. Okay, so there's no calip-hashing.cc file. So we move that to the trash bin and continue with the next header file, which is the frame precalc.header file. This is a short one. But an important file, which is responsible for the following. In the inverse depth parameterized bundle adjustment, an observation is related with two frames, the host and the target. But we just need to compute once to each two frame pairs, not each observation, and this structure is used for this pre-calculation. So this means if we have two frames, we can of course go from host frame to target frame, and we could also go from target to host frame. But to my understanding, this is only done once, namely from host to target frame. So this is related with some transformation. So there will be many matrices related to rotation and translation, to calibration, rotation, calibration inverse, and so on and so forth. Let's create the implementation. By creating a file called frame.precalc.cc. And the only method that is implemented in the CC file is the set method. Okay, let's add it. Let's add this file. It is located in internal. Frame precalc.cc. Okay, the next file we will create in this internal folder is the frame Hessian.header file. The almighty frame Hessian, which we have been using a lot in the code we already exposed or explored, I mean. And this is where all the important state variables are contained. And given what we have seen so far in the other code parts, we can already imagine that this takes a very important role in our code. So the frame Hessian will have, for example, a frame ID. It will have an associated frame. It will have this DIP, which is the IP of I is the ith pyramid, with DIP I0 is the original image, whereas DIP I1 is dx, 2 is dy, and by default we have 6 pyramids, so we have DIP 0 to 5, and this will be created in make images. So make images will also be a method here, like this one. Create the images and the gradient from original image. So we will have the original intensity image and the change of intensity in X and Y direction, it seems. And this is not implemented in this header file, therefore I think this will be implemented in the CC file, as it should. So let's add a frame hashon.cc file. And let's move the code here. And here we have the make images, which will create this DI or DIP image. 0 is the color. And 1 is the X and 2 is the Y. Okay, this was the frame hashon. It was an internal frame hashon.cc. Frame hashon.cc. Next we have global calib in the internal data space. Here in this header file, global calib and global funcs. We already have those two files, so we can continue with the next one, which is called imager point.h. Okay, so this is the imager point data structure. And we'll see that we have an imager point temporary residual. The residual of imager point for solving optimization problems on imager points will be converted into a normal map point residual if the imager point turns out to be a good point. So the imager points, the goal is to have our imager points converted into a map point, to a valid point, we could also say. This is not always possible, that's why we have imager point statuses like good, OOB, outlier, skipped, bad condition and uninitialized. Okay, the implementation is needed. So let's add a new file called imager point.cc. Okay, so here we have the constructor of the imager point. Which will also already evaluate the pattern, the residual pattern, it seems. Okay, but then we can trace on a specific frame. Then we have some Chinese characters again. Let's see what they tell us. Ah, that's interesting. Okay, so step 1 is check the position of the point on the epipolar line. This was just only a few characters for such a long explanation. And then check eye depth and closest distance. Okay, then we have this comment. Which tells us the furthest distance. Note that it may be infinite. Then we have a large comment here. Calculated according to the farthest distance, the projection in the current frame. Okay, also makes sense. Then we have this part. Called finite distance and finite max depth. Then we have 2 pixels on the epipolar line are very close together. And here we have any distance. Okay, compute error bounds. So the imager point has quite a few functionality. But now we can add it here. Internal imager point.cc. Then we will have to add in the internal folder another file called index thread reduce.h. LDSO Twitch. And here we have multi-threading tasks. Use reduce for a given task. Let's say not multi-threads, but to parallelize a given task, like removing outliers or activating points. Okay, so this is related to multi-threading, which we should not bother at this moment. And this is a header only file. So let's continue with the next file, which is the point Hessian.header file. Come on. Okay, so let's add Twitch here as well. And the point Hessian is the internal structure of a map point. Okay, so similar as with the other Hessians, frame Hessian for example, the point Hessian will also be very important for storing additional information about the inverse depth, the inverse depth 0, scaled, and null spaces as well. And some step information about, not about, but for the optimization. and will also have a color in the host frame. Okay, so with this point hashing, we also need to create the implementation point hashing.cc. Point hashing.cc. Which is very simple, probably the most simple file. This is everything. It's just the constructor, which takes in an integer point and creates a point hashing out of that. Okay, so that's it. Let's add it here. Point hashing.cc. Next file we need in this internal folder is pr.h. And obviously it's not in the source directory, but I will move it to the include directory. So the PR header file is again a little bit longer. I mean, the implementation is still missing. But actually the header file is longer than the implementation. This is because the header file will contain definitions related to G2O, so to the optimization, and it will override G2O types, for example, this base vertex. The reason is that the LDSO is using a little bit modified types to define, for example, the SE3 rotation and translation data, and doing some other LDSO specific stuff. I even think this reading and writing is a custom idea of them, but I'm not sure. Overall, it is necessary to override these base classes with the custom implementations of vertices, edges, to create this this final pose graph that should be optimized during, for example, the loop closure thread while it is running. So this is what in PR is defined, or what PR is defining. Let's add the implementation. New file pr.cc. And let's add the code. So it is a bit shorter than the header file because it's just implementing specific methods to compute the errors of the edge IDP prior, the edge PR IDP, and I think the edge project pose only and the edge project pose only sim3 data types. So this is important, and we also add it to our CMake lists. And next we will have another header file in this internal space called raw residual Jacobian.header file. And Jacobians are a very important part because they contain the first derivatives of our energy functions, or the cost functions, and they allow us to know in what kind of direction we want to optimize to get the minimum or optimum of a specific cost function. And there's a bunch of Jacobians used in optimization, as the comment tells us. And here are just shorthands for those Jacobians. So we have dx and y divided by dxi over the camera, over the eye depth. So we have specific combinations of the derivatives. This will probably also be a very interesting part to look into, how the Jacobians are calculated. So therefore we need this file for that. Okay, do we have an implementation for that? No, we do not have one. And similarly, we'll have another header file called residual projections.h, which does not have an associated implementation, but only this header file. So we can derive the eye depth here, the inverse depth. We have this projection equation, which I think I saw multiple times in different places. And PTP is probably point to point. Project one point from host to target. Okay, this is very important to be able to do that. Project point is the method, which takes in several parameters and returns a 3D point. No, a boolean. Okay. So the point, the transformed point, will also be output somewhere here, probably. Yeah. Another function to check while running on a dataset, as many already. Okay, so we have this raw residual Jacobians, or Jacobian, and residual projections.h, which we just created. And we have another file here called residuals.h, which we need to add as well. Residuals.h. So besides the Jacobians, another major part in the algorithm is of course the calculation of residuals, which tell us, for example, the photometric residuals tell us how good or how bad we currently are given a specific cost function. So the cost function itself is the residual. This, you can imagine it being like a score that tells us how big or how small an error is. For example, when we take the two images, host frame and target frame, and we subtract them from each other, if they are identical, then the resulting residual should be 0. Otherwise, it will have a specific value. And this is being done here for the photometric cost function or error. Next we have to also create the implementation residuals.cc. There's a lot commented out here. And there is a Chinese comment. Let's translate. And tells us that the current state is already outside. Which probably means, I think this is probably a translation error, out of bounds. Let's put it into quotation marks. Let's see what this X and Y means. Oh, that's interesting. So this is the derivative of Lie algebra to xy. And this one is the derivative of Calip to xy. And this is probably the connection of xy and I depth. Let's see. The derivative of xy to I depth. So we have the derivatives here because we are dealing with residuals. And those are the basis for the residuals. What did I just say? Okay, the cost functions are the basis for the residuals. Let's see, here we have various derivatives like diff di depth, diff calip, and something related to xy again. Derivative from xy to Lie algebra, see lecture 14 for the form. Lecture 14. Of what source? Okay, so the rest is commented out anyway. So let's keep it like that, and let's add this here, internal residual.cc. All right. With this, we have finished the internal top level directory. But we are not finished yet. We still need to add a new directory here in the internal directory and call it optimization backend. And we need to do that in the include directory as well. Oh, this should be a folder, not a file. Like this. And here we need to add the last 4 files. The first one is called accumulated sc hessian.h. Okay. I just deleted my code here. Okay, let's add the signature of Twitch here. And let's see, we have a constructor and a destructor. We have a set 0, stitch double, add point, stitch double, empty, which stands for multi-threading. We sum up results, add points internally, and stitch double internal. And this is everything that's being done here. And we need the same in the source directory. And we call it accumulated sc hessian.cc, not h. Okay, so stitching is basically we have a vector, and in this vector we adjust the blocks and somehow combine them. And there is this block. I think it's a method. Yes, it's a method of this matrix data type. And there's also a segment method, like here, for example. And we just combine those block and data within a matrix or vector. Okay, so let's copy the name. And let's add a new area here called internal. And then optimization backend. And then this name. Okay, let's add the next file, which is called accumulated top Hessian. Accumulated top Hessian.h. Let's copy the name. And let's put it here as well, with a CC ending. And this is the accumulated top Hessian if it is not deleting it for some reason. This is the accumulated top Hessian.cc file, which also includes this SSE2 optimization instructions. And this is one of the tricks why the LDSO is running in real time, because the backend, the optimization backend, is highly optimized to be quite efficient in the calculations. And this is why at some point we might see a comment that tells us what we should do with this backend. Let's see if we can find it. Let's add this file now to the CMake lists text. Not the whole file content, of course. Okay, I think we will have one more CC file, but two more header files. Let's see. Okay, here we need to add a new file called energy functional. To be honest, I was missing this one already, because we saw it from the beginning in the full system, but it took so long to actually create that file. Okay, so let's read through this interesting comment here. So the energy functional.h is the overall interface of optimization. The full system class will hold an instance of energy functional and perform optimization steps through this interface. I moved all the E-frame, EF point, EF residual data into frame Hessian, point Hessian, and point frame residual, because I think they are the same. I don't know why DSO designs such an optimization backend beside the full system and keep its own frames. Residuals, points, which are already stored in full system class. Here you still need to add, delete, margin all the stuffs and keep them synchronized with full system. Looks not good. Maybe for some historical reasons. So this is something I think we have seen quite a lot already, that data is just copied and stored across many classes as duplicates. And this is a pity, because this makes it unclear where we need to change something in order to see the effects in the algorithm or when running the algorithm. This was actually something that prevented me from adding the ground truth data into the DSO. So DSO, I would say, was a little bit more, I don't want to say chaotic, but a little bit more complicated. And this has not really improved in the LDSO, which makes it a bit hard to understand the code base. But yeah, that's why we are here, right? In this energy functional, we have friend classes, because only friend classes can see your private and protected member variables. So here we can insert a residual, we can insert a frame, drop a residual, marginalize a frame, remove a point, marginalize points F, drop points F, and solve the system, calculate the energy, make indices, set delta F, set adjoints, and we store some data about the frame hashing, the number of points, the H matrix, the B vector for solving the system of equations, the last null spaces, here we have get stitch delta F, where we add or we increment, we iterate over the number of frames and then multiply that by 8 to add a segment of 8 elements, starting with C parse, with the end of C parse. We add the delta of each frame here in this function. But as the comment already suggests, I really don't know what they are doing in the private functions. That's why they are private, probably. And here we have specific data that is related to the energy functional. That is the optimization. And one can already see that this is quite cryptic as well. We have this ACC, which is the accumulator, and then we have the SSE, which is this instruction set for optimizing the code, and then we have a top L, top A, and a bot, and we have a prior and delta F, and several other functions with multi-threading capability. Yeah, there's a lot to take in. But this is one of the important parts of the LDSO. And this is the second to last file that we need to create. And now we need to create the last. And the last file is called matrix accumulator. Accumulators even. And I think I forgot to add the energy functional.cc file. Yes, let's do that. simple as that. Just copy and paste. And this is a lot of code again that is doing some important part. It's playing an important part in this algorithm, and it's really, it makes me a bit, maybe not sad, but I'm thinking about why the heck is this, or must this be that complicated? It's probably, some part is probably due to the use of C++, but really many things are just, many things are related to management as well. So you have those many frames in the video sequence, and you somehow need to keep track of the frames, of the features, of the points, of the 3D points, of the 2D points, of the descriptors. This is very complicated, and I'm just asking myself if this really does have to be this complicated, or if there is some hidden way. Maybe the research community does not know, which makes the whole creation of Visual SLAM systems a lot easier without all those, I have to admit, interesting parts, interesting math, but it's still, it seems like a lot of hassle to do for a simple task of just estimating how the camera is moving and the 3D world is structured by using image data. It's just too complicated for me. But let's not get philosophical here, but rather continue with the last files. So this is the energy functional.cc file, and we have this matrix accumulators .header file, which is a file I'm really happy I do not have to type. It has 1700 lines of code, and it's basically just a multiplication and addition of values, as you can see. Very, very cryptic what is happening here. But let's make it a little bit less cryptic by adding a Twitch string here. Okay, and this brings us to the final file that needed to be created. I think we should have every file in place now, and let's now do a final check of the CMake lists file, if we have everything included there. Obviously not, because we need to add the energy functional.cc file. And let me now quickly go through this list and see if everything is in place. So with a camera, we have a frame. Okay, it's sorted differently. Let's keep it like that. Like, we have a map, we have a camera, we have a setting. Okay, in our case, it's called settings. In the original code, it's called setting. Map, camera, setting, and point, frame, and feature. Okay, this is here. Then we have a point Hessian, we have a frame Hessian, we have a global calip, we have a frame precalc, we have residuals, we have imager point, and we have PR. Okay. Then we have our optimization backend with accumulated sc hashen.cc, accumulated top hashen.cc, and energy functional.cc. Then we have front end cause tracker and cause initializer. Then we have the full system. Then we have the DSO viewer, the feature detector and matcher, loop closing, pixel selector 2, undistort, and image RW OpenCV. Alright. This should be everything. Let's now, after this configuration using CMake is done, let's now try to build this this project. Let's see if we get any errors. It might take a long time, and hopefully it will not crash the stream as it did the last time. Let's just hope for the best. Okay, so the build has finished with exit code 1. Is this good? I'm not sure. It's hard to spot any errors. Map.cc, and here it failed with map.cco. Why did it fail? Okay, here. In full system. Expected identifier. Okay, this is something I really screwed up, it seems. Was not declared. Oh yeah, I think I know, because I was not finished with full system. There's the full system. Yes, here I have, in hindsight, commented out all the important stuff. Which I did not have back in the days, but now I have. So let's change that here. Okay. And with the rest, I think we should be fine. Okay, let's try to rebuild that. Hopefully the errors are now gone. But I saw some errors regarding some commas and semicolons, I think, which will probably persist, and I need to fix them. But hopefully they will be easy fixes. Let's just take a cup of tea. Oh, I think it stopped. Okay, we still have error code, exit code 1. But it's a pity that I do not see the errors here clearly. Those are only warnings. Okay, for example, we have an error here. Okay, there are many errors. Failed map. Okay, let me quickly go through the errors. So in calipation, here, error scale F inverse was not declared in this scope. Okay, where should this be? In the settings.header file, probably. Okay, here we are. Let's compare that. Okay, it seems that I really missed the other variants. So I will just copy and paste them here. So what was missing is in the settings.header file, we had the inverse versions of the scale idepth and scale xrod and so on and so forth. So there's also an inverse version where we simply divide the values by 1. We divide 1 by those values, I mean. So this part was missing. I don't know how I could overlook that, but given the sheer number of settings, I do not blame myself that much. A little bit, but not that much. Okay, let's now continue the build process or